Yes, here we are. This is Physics 105A. Video lecture 6. And I'll start out with some announcements. So lectures 5, 6, and 7 are for the week ending Friday the 4th. April 3rd. 4th through 20, April 3rd. Okay, so that's the Friday before spring break. And so we'll want to have the homework in by then. Homework 8, which I seem to have received most of those, or some of them, ended with the length of the cycloid and the helix. So some people included some of those gradients and stuff from the next homework on there already. And there was a little bit of ambiguity maybe, and some of the things weren't done quite right. So I'm going to give a little more guidance on these. It's the central force type of problem, and the gradients and other vector expressions that go with it are very typical. You'll see them again in electricity and magnetism. So we're going to get a little head start on that. So I think that's what I'll do first, is give a little more guidance on and resolve some ambiguities on what was going on right there. Yeah, anything else? So yeah, 5, 6, and 7. After the spring break, we'll have a couple lectures and then an exam. So we have plenty of time, mainly those 2 first lectures, to regroup, do review, and get everything figured out. Okay, so for today, for this one and the 7th one, I want to make it into Newton's law of gravity and the Kepler problem. This is some preliminaries. Let's see how far we get. Okay. Here's what we had for some of these homework problems. I was asking for the gradient of R, the gradient of f of R, and then the divergence of the gradient of f of R. And there may have been some ambiguity because we were using F for the force. So here, F is not equal to, I won't put it that way. F is not, here, not F equals F of R over R. So we were using this function F of R as the scalar part of the central force, and this was just the direction. So it's not the case on these expressions. What we're talking about is simply a function, a scalar function of a real variable. Okay. Function of a real variable, but it turns out that this R is, of course, the magnitude of the vector, of the position vector. So this is anything. This could be the potential function for it. It is any function. So, but rather, F equals F of R, scalar function, okay. Real function, okay, just so any function. Okay, so we did this one already. I'm just going to repeat it. I think I'm going to go through all 3 of these just to make sure people see this, and then you can practice it on your own. I'll do it with some indices. This one, first of all, of course, we know the gradient is those 3 derivatives, but if we just take the, here, let's add this. Of course, R was root x1 squared plus x2 squared plus x3 squared. So this is any function f, but that's what the argument means here. Now, good, so if we do dr dxi, dxi of this expression here. That's what I did the other day. Okay. Then what do I have? I've got 1/2 this thing down here, and then the chain rule gives me 2 times whichever x sub I, okay, I'm differentiating with respect to. So 2x sub I, the 2's cancel, and what I see, that's x sub I over r. So this is useful to hold on to, and of course, if you take all three of them, you're going to have the entire vector over its magnitude. So this result and the individual one, x sub I over r, those are both equally important and useful. You do this a few times and you have this in your repertoire. Okay. Yeah. Now, so for the gradient of f of r, okay, this is the one we want to start on now. Be careful. So again, I'm looking at dvxi of f of r. And then once I get this, I'll just bundle all three of them like I did down here. Right? This is a vector right here. So that's just going to be the chain rule. F prime of r times d dxi of r. But yeah, now we know this one because we just did it there. So equals f prime of r xi over r, and therefore we have for the gradient f prime of r times this unit vector. Okay. Useful comes up all the time. Okay, so now we're ready to do the divergence of the gradient of f of r. So the divergence is going to turn a vector into a scalar. The gradient turned a scalar into a vector. Okay, so we're fine there. You know, erase this. And we'll set this one up carefully. So I'll get some space here and just put our results in place. So we have d dxi r xi divided by r. We have d dxi f of r f prime of r xi divided by r. So those are the basic results so far. Now we want the divergence of the gradient. I'll work right off of this expression here. So first of all, by definition, that would be d dx1 times the one component of the gradient of f of r. So the one component of the gradient of f of r is this one here if I let I equal 1. So I'm looking at f prime of r x1 over r. And yeah, then from the definition of the divergence, I'm just doing with 2 and 3 as well. d dx2 f prime of r x2 over r d dx3 f prime of r x3 over r. So another way to look at this, if we were using an index notation, we would be summing I equals 1 to 3. And by the way, this is also an interesting problem if you go for, if you have an n component vector. Okay. Because then you'll see the actual dependence of this on the number n, whereas here we're just going to have n equals 3. Yeah. And then what would you have? You'd have d over dx sub I of this f prime of r x sub I over r. Okay, so that's 1, 2, and 3. So let's try this. There's a bunch of chain rule going on here. So we would have summing here. Now we're going to hold these two constant and just take the derivative of f prime with respect to xi, so we're going to end up with f double prime of r, and then the chain rule is going to bring down another x sub I over r. Just like we did there, but we already had an f prime, so we have f double prime. X sub I over r is already there though, so it's going to be x sub I over r, the quantity squared. Yeah, then for the next one, let's hold these two constant, and we've got our x sub I, we differentiate, and we just have f prime of r divided by r. And for the third part of this whole chain rule, product rule, we have plus f prime of r x sub I, and now we have to do d dx sub I of 1 over r. So we're going to get a minus 1 over r squared, and now the chain rule comes in, minus 1 over r squared, and then x sub I over r, again, because 1 over r itself is a kind of an f of r, so, and then x sub I over r again. So now we have to sum this whole thing up. Summation. And this is going to be interesting as well. I'm just going to mention it. So at this point, we're summing over I. We can actually pull f double prime over r squared out, and then the x sub I squared, 1, 2, and 3, turns into r squared. So x of 1 squared plus x of 2 squared plus x of 2 squared is equal to r squared. So what we get here for the first one is just f double prime of r. Now when we sum over this, there is no subscript, but we're still summing I equals 1 to 3, so we have to add this one in 3 times. It's here for every one of these. So we have 3 f prime of r divided by r, and then down here we're going to have minus f prime of r over r cubed. So we can pull out f prime of r over r cubed from right here, and then we would be summing minus xi squared from 1 to 3, so that would give us a minus r squared over that r cubed. So we're going to end up with minus f prime of r over r. So the final answer here is f double prime of r plus 2 f prime of r divided by r. So that's a formula that you can actually use. And since I did this for you, I'll just add to the homework. First of all, it's still on the homework. You want to go over it carefully and make sure you see what's going on. You could generalize to n. So you know what? I'll add this to the homework since I did this thing for you. The following. So homework, apply this formula here, star, to f of r is equal to 1 over r. Okay? That's very important. That's the Newton potential, the Coulomb potential, okay? And you're going to find, interestingly, that the thing vanishes, but it's a 0, but it's not just any old 0, okay? When we end up looking at del squared of 1 over r, which is what this is, yeah, that vanishes, but it's not just any old function that vanishes. It's actually going to be a delta function. And so we'll look at that again, but it's a good exercise to have done. So good, apply this to f over 1 over r. Also, calculate for the case that x is equal to x1 all the way to xn, and you know, x squared equals x dotted into itself. It's just this whole thing integrate summed up from I equals 1 to n. x1 squared, xn squared. So yeah, it's this problem summing up from I equals 1 to n instead of 1 to 3. It's, you know, it's interesting to look at. Good. So the other ones, the curls, have at it as well. I already made some discussion of those. Okay, yeah, this is worth doing. So if you're unfamiliar with these, there's a bit of chain rule and stuff. We're monkeying around here, and we want to make sure we get it right. And this becomes part of your repertoire. Okay, what next? What's next is a little bit of review, a little bit of discussion where we're headed, and then I'll just look at the clock and decide how far we want to go. Good. So, review. We're in this central force problem, and I'll just, more briefly than before, write down what we had. We had Newton's law for a central force, right? We saw that we can get a potential energy function well defined like this. We had energy conservation and conservation of angular momentum in the system like this, so that we ended up having m r squared p dot equals L as one of our conserved quantities, and 1/2 m r dot squared plus L squared over 2 mr squared plus u of r equals E. So these were our two, and the E is also equal to a constant. So E and L are our conserved quantities in the problem. We're now using plane polar coordinates. Plane polar. And we've studied this thing here called the effective potential. And by doing that, we can actually just focus on this for a while. It's the radial equation, one-dimensional type of problem. And the effective potential had this look to it, depending on what your potential is, but you're often going to have some kind of local minimum. The local minimum corresponded to a circular orbit, so we already had an analysis there, and that corresponded to a certain energy value, and then the higher energy value, the value of R now went between a maximum and a minimum value, and the motion itself took place inside of an annulus if you were back in the XY plane, back in your two-dimensional problem. So you could have motion doing something like this. And these are fun to draw if you can, but I can't. Okay. Yeah. So that's how far we had gotten. Now what we want to do next is investigate this is the potential, the 1/r potential, whose derivative gives you Newtonian gravity and Coulomb's law. This is what we're after. So I'll just write your Newton gravity. And Newtonian gravity, of course, solves the two-body problem. It solves the Kepler problem. And so I could just keep going and systematically do this problem and then talk about Kepler and so forth, but instead I'm going to stop here, knowing that this is where this heads, and discuss Kepler's laws, because Kepler's laws were discovered before Newton was born, right? Newton was born when Galileo died, and I think Kepler died before Galileo. Okay? And Newton used Kepler's laws in order to infer and discover the inverse square law. Okay? So that's actually a famous moment in history. And we may as well take it in that order. Okay, so here's what I'll say. Next leads to integration of this here, which we're going to call star, and the conic section, and just the conic sections. The trajectories here turn out to be conic sections, so you have ellipses, circles, parabolas, hyperbolas. They lead there, and I'll say i.e. Kepler's laws of planetary orbits. Planetary orbits. So that's what I'm going to do, and that'll take, who knows, it will take the rest of this hour, maybe a little more. And once we have that, then we have to do, we reduce the two-body problem to one body, and when we do that, we actually arrive right here, and then we'll go through the whole program. Okay. So this isn't so much a detour as it is a historical catching up. I have to do it sometime, and so I'm going to do it right now. Okay, so two-body problem to one-body problem. Okay, so let's get started on this. So this is just a short historical excursion. So first of all, Kepler inherited Tycho Brahe's data for the orbits of planets, naked eye observations. Kepler inherits those data, he analyzes them, and he's able to come up with the laws of planetary orbits. So Kepler's laws 1, 2, and 3 of planetary orbits. So yeah, what's the first law? The first law is that the planets, the orbits of the planets around the sun are ellipses with the sun at one focus. So planetary orbits are ellipses with the sun at one focus. And how many planets did Kepler have there? He probably knew them out to Mars or Jupiter. Outer ones hadn't been discovered, with the sun at one focus. Okay. So I brought some magnetic things here, and I wanted to plop them on the board and draw some nice ellipses. That's part of the presentation. But the board doesn't hold a magnet to it, so I don't have that. But it's something to just show you guys. You can do it at home in your spare time. You probably know this. So you take a loop of string, and these are your two foci, right? These are your two foci, and you have that string hanging there with the two foci, and then you have this point here. Here's your chalk. Pin them down right there, and then you just run around and keep the sum of the distances constant. That's the definition of the ellipse, and you draw out this beautiful ellipse. You can never do it as well by hand, you just get some weird oval. But anyway, that's what Kepler found, and what I will do is just draw one of these hopeless ellipses. You've got the sun at one focus, and you've got nothing at the other focus. and the planet is orbiting the sun. Okay, so there's one focus, there's another, this is the sun, that's the focus where nothing is at, and you can label this ellipse. You've got A is the semi-major axis, and B is the semi-minor axis. And if you bring these foci close together, of course, the ellipse just turns into a circle. And in fact, if they're pretty, if they're not even that close together and you do the construction with the string, it's going to look pretty much like a circle. Very close to a circle. But far enough from a circle that Kepler couldn't fudge it. The data showed that, he couldn't fit his data from Tycho Brahe into a circular orbit, and other problems, and other ones as well. Good, so that's the law. That's the first law of planetary orbits. Do 2 and 3, and then we'll have something to work with here. So the second law of Kepler is called the law of areas. And that says that the radius vector from the sun to the earth, I'll just say R, sun, earth, as the planet orbits the sun, and there's nothing at this mystery spot here, it's just one of these little foci. It sweeps out an area, right? From here to here, it sweeps out an area. From here to here, it sweeps out an area. And what Kepler found was that the radius vector sweeps out equal areas at equal times. Sweeps out equal areas at equal times. Sweeps out equal areas in equal times. Okay. Good. And the third law is the law of periods. And the law of periods says that for all the planets, out to Jupiter, I suppose, at the time, because I think this is the last one he found. What would be? 1, 2, 3. For all the planets, period squared over semi-major axis cubed is equal to a constant. And the idea was it was the same constant. So if you took the period of Mercury over its semi-major axis, this one squared, this cubed, you'd get a constant. You did it for Earth, Mars, etc., Venus. You'd always get the same constant. Yeah, so it's nice to think of this constant. Just let T be the period of the Earth orbiting the Sun. 1 year, call it 1, and let the semi-major axis be, the distance from the Earth to the Sun. It's close enough to a circle. Just take that, or take the average distance if you want. As your unit of length, then you can have 1 over 1, and the constant would be equal to 1. Okay, doesn't matter what the constant's equal to. This relation's always going to hold. So that was Kepler's third law, and I'm going to use this in a bit. For a circle, we would say, for a circular orbit, we would say T squared over R cubed. Okay, and remember the planetary orbits are nothing as stretched out as this ellipse. They're very, very close to a circle as far as if you were just to look at it, it would look like a circle. Okay, so those are Kepler's 3 laws. Now, Isaac Newton inherited these laws. By the time Newton was doing physics, these laws were well established, but they were not dynamical laws at all. They were just established empirically, so to speak, by fitting data. And I guess one would have to say they were seen to work well. I mean, this is just an amazing accomplishment. This is all done by hand. And I have in a book actually a quote where Kepler announces the discovery of his third law. And Maybe I'll bring it around sometime. It's an amazing piece of excited oratory and rhetoric. It's unreal. He was, suffice to say, he was amazingly pleased with this result, and rightly so. Okay, but so Newton inherits these laws, and in the meantime, he's set up dynamical laws. And so the next analysis is how Newton used these laws and the laws of motion as formulated by him in order to infer the 1/r² gravitational law. So next I'm going to go here to Newton. And the first thing, the story with Newton sitting under the tree here actually has some good meaning. Okay, with Newton sitting here reading his book. Big wig. Because the meaning of the story is that there's this apple, there's also a moon out there. Okay. And the meaning is, or the idea is that the apple and the moon obey the same dynamical laws. The same law of nature that governs the fall of the apple governs the orbit of the moon. Okay. Obey the same law. Okay. That was not Kepler's standpoint because those laws hadn't been discovered yet. Kepler just found what those laws were descriptively. Okay, so here's our moon. So that's the same thing. So that's one. I'm going to go ahead and number these ideas. Then the next thing is to consider M orbiting M. Okay, so now we've got a central body, capital M, but we've gone to smaller body orbiting it, and see what this means here. So you're going to say, what is the force law? Question mark. What is the force law? And the first thing we would, if we were Isaac Newton, the first thing we'd do, the force has to be proportional to m. And that's simply the law of free fall. So the apple obeys the law of free fall. You know, if this is now the moon around the earth or the earth around the sun, it's got to be, you know, law of free fall is F is equal to mg. Okay, so F has to be proportional to m by the law of free fall. Immediately after that, F has to be proportional to capital M because the relationship is reciprocal. That's by Newton's third law. Okay. Newton's third law. Newton's third law. Okay. And then, looking at a circular orbit, you can say F. See if I can get this all in one line. Okay, looking at a circular orbit, you can say F is equal to mv squared over r. That's simply the expression for circular orbit centripetal acceleration, mass times acceleration. So that's Newton's law and the properties of a circular motion. And now watch this, m over r. Now this v can clearly be written as 2 pi r over the period t squared. Okay, so I'm going to pull out the 4 pi squared m, 4 pi squared m, and I'm left with r over t squared. Okay, but this is proportional to, let's ignore the 4 pi squared m, this is proportional to r over r cubed, namely by Kepler's third law. So that's where Kepler's third law came into the analysis. Proportional to r over r cubed, which is, of course, 1 over r squared. Okay. You heard it here first. So that is how the inverse square law is inferred, and then Newton generalizes that, calls it universal gravitation, says any 2 point masses are attracting each other according to that law. Okay. And some other things go into the mix as well, because if you have extended bodies, you have to prove mathematically that the force law for spheres is center to center. In other words, this R for 2 spheres, 2 uniform spheres, is measures from center to center, which we'll do next semester. It's no big deal. It's an interesting problem. You can do it using Gauss's integral theorem or some other things as well, Gauss's law, or other methods as well. Okay, so other stuff came into the mix as well, but that's where the universal gravitation came from. First, he had this for the orbits, okay, and then generalize it to universal gravitation. So I'll put that up here. So 3 is this numbering things 3, 2, this was 3, and then I'll just say, I'll formulate it in the universal gravitation. Okay, so Newton universal gravitation and we would say that the force, so we have 2 point masses, 2 point masses, M1, M2 separated by a distance r, and the force magnitude is some universal constant product of the 2 masses divided by r squared, and I'll just write attractive. There it is. Attractive central force. Along the line joining them. So yeah, that, and it took some time until this constant was actually determined. Cavendish determined the value of this constant. So, now I'm talking about 2 point masses, and now if we wanted to take this insight and make our way back to proving everything that Kepler discovered using dynamics, then we actually have to start with 2 point masses and a 2-body problem. So from here, we go to the 2-body problem, and it's going to take a few steps in order to actually get to what we've had on the board as our central force problem. So the 2-body problem, I'm just going to set it up. I don't think I'm going to run this out too much longer. So the 2-body problem looks like this. You've got M1 and you've got M2. And they have their respective positions, R1 and R2. R vector and R2, those 2 positions. So what we're going to do is define a vector R is the difference of these 2 vectors. And it's going to turn out that we can express the force law just in terms of this one vector. It'll be a little bit of a few steps until we get there, but we'll express it in terms of this one vector the mass in our Newton's law that we had before, the mass in our central force problem is actually going to be what's called the reduced masses, a particular combination of these masses. Okay. And the motion of the individual vectors will then be measured with respect to the center of mass. So that's what we're going to do next. We are going to express these two vectors in terms of this difference vector r, and then we'll work our way through. We'll turn the two-body problem, which is right here on the board, two masses out in measureless space, attracting each other by Newton's law. We'll take that, turn it into effectively a one-body problem again, then we'll go back into what we have been studying before. Okay, so that's the plan. I'm not sure how long I've been going, but I'm going to call it quits now. You guys get that homework, and so whatever I do for the third lecture of this week, that homework will go on to the one after the spring break. Okay, good. See you next time.